Chapter 9, Section 5, Applications Using Linear Programming. So we've actually done applications with linear equations and look for specific ordered pairs to be solutions to two linear equations and those kinds of things. Well, when we get into inequalities, there's a lot of things that can happen. In fact, this is where we can get very complex systems, and they take on a couple relatively complex systems to show you where algebra can really be useful. And in programming, they do linear programming in business all the time. So there's going to be some terminology here, so you can make sure that we can try to get on the same page, because there is a lot of translation from English to algebra. So first they describe linear programming. Just to read it to you, often a quantity we want to maximize depends on two or more other quantities. For example, a gardener's profits P might depend on the number of shrubs S and the number of trees T that are planted. If a gardener makes a profit, a $10 profit from each shrub and $18 profit from each tree, the total profit in dollars is given by the objective function. Profit P, right here, is equal to 10 times S for shrubs. That's a $10 profit per shrub, plus 18 times T for the $18 profit per tree. So if you had one shrub and one tree that grew and you sold them, you'd have a profit of 10 plus 18, or $28. Well, now when you look at that just in itself, you say, well, why not just grow all trees and do those kinds of things, because that's the highest profit. Well, there's probably some other conditions you need to deal with. So let's go on here. Thus, the gardener might be tempted to simply plant lots of trees, since his yield is a greater profit. This would be a good idea if it were not for the fact that the number of trees and shrubs planted, thus the total profit, is subject to demand or constraints. So you could end up, if you grew all trees, you might end up with a whole bunch of trees left over, and those kinds of things. For example, to improve drainage, a gardener might be required to plant at least 3 shrubs. Thus, the objective function would be, in this model, would be that the shrubs need to be greater than or equal to 3. Okay? Because of limited space, the gardener might also be required to plant no more than 10 plants. So the total of the plants would be the shrubs plus trees has to be less than or equal to 10. And finally, the gardener might be told to spend no more than $700 on plants. If the shrubs cost $40 each and the trees cost $100 each, the objective function is subject to a third constraint. Remember, these are constraints, these inequalities. They're narrowing down the possibilities for my other linear stuff, right? Well, here's an equation or an inequality to represent this third constraint, which is the cost of the shrubs, which is $40 per shrub, or 40s, plus the cost of the trees, which is 100 T, or 100 times the per tree, right? Depending on how many trees you have. Well, this needs to stay less than, when we sum this up, needs to stay less than or equal to $700. In short, the gardener's wishes to maximize the objective function, here it is profit, right? Going back to the original, profit's equal to $10 per shrub plus $18 per tree. But it's subject to these constraints. Has to be, the number of shrubs has to be greater than 3. The number of shrubs and trees together needs to be less than 10. And the cost of shrubs and the costs of the trees are summed up here have to stay less than $700. Shrubs, you can't go into the negative, so the other constraints, now they don't talk about these constraints, but if you think about that, it's kind of like when we go into when we've solved and by factoring some things that have to do with distance, we end up with negative solutions. Those are not possible. And that's the same thing, you can't have a negative shrub or a negative tree. So the number of those has to be either greater than or equal to 0. A lot of times this implied constraint won't be talked about in your model or into the word problem you're talking about. But you need to think about that. Is it possible for these things to be less than 0? These constraints form a system of linear inequalities that can be graphed. The gardener's problem is how many shrubs and trees should be planted, and subject to constraints listed in order to maximize profit. To solve such a problem, we use a result from the branch mathematics known as linear programming. And the corner principle, suppose that an objective function f, right? We're going to have this machine that's going to kick out values. That's what a function's like. And we have these inputs of x and y in this case, dependence on these x and y. And in this representation of this function, they're saying, well, a, b, and c are constant. Suppose also that f is subject to constraints on x and y. Which form of a system of linear inequalities, if f was a minimum or maximum value, then it can be found as follows. One is to graph the system of inequalities and find vertexes where these things overlap, basically at single points. Two is find the value of an objective function at each vertex. The greatest and the least of these values are the maximum and minimum of the function respectively. Now, let me say that again, is basically we have functions, but under constraints you're going to have a maximum value, which could be a good thing if you're talking about profit, or if you're talking about loss, the minimum would be the thing you'd probably be looking for. The ordered pair xy at which the maximum or minimum occurs indicates the values at which the max and min occur, right? Okay. So they're taking this principle that, hey, we can find pertinent information by graphing this stuff. So example 1, we take this gardener's problem and discussed above with those constraints. Here's that equation, and P equals 10S, which is the profit from shrubs, $10 per shrubs, plus 18T, which is $18 per tree. Here's our constraints again. You have to have more, 3 or more shrubs. The plants can't be more than 10, but it could be equal to 10. The costs here have to stay under $700. It costs $40 for a shrub, $100 for a tree, and these things have to be either 0 or positive. So we have these constraints. Number of shrubs has to be greater than or equal to 0, and trees greater than or equal to 0. Well, they're going to take some things in here. When we graph this system, we can graph all these inequalities with shading, and that's what this graph is trying to show here. Now the portion that is shaded represents all pairs that satisfy constraints is called the feasible region. So they're talking about this region here. Notice that every one of these constraints and are graphed in here. Now this isn't a graph of our original equation. Here is S has to be greater than 3. We had to have that many. S also has to be greater than 0. And so does T needs to be greater than 0. This is the gradient of T, and this is S, right? So here's the line right here for T is greater than 0. And which one's? Oh, the blue one here is S plus T is less than or equal to 10. Notice they got these arrows coming off the sides of these lines. That shows you the shaded region. If it was just this inequality, it would mean in this blue line everything on this side or this half plane of that split by this line here would be shaded. So, and then here's our last constraint, is this equation or inequality, excuse me, is shaded down here. Well, when I take all these shaded of these lines and just consider where the overlap is, here is this feasible region they talk about. Okay, and they start looking at this deal to look at. They also go in here and say, well, if we take the lines represented, like from the line that's represented by this red one right here, and the line is s equals 3, we look at this line, we can get an ordered pair, which in this case would be 3 for the s value and 5.8 for the tree deal. This is shrubs and this is trees. Remember, in ordered pairs you put in the value for the horizontal change, and the second number is a vertical change. Well, this is say, let's look at this vertex B right here. Well, this is where these two lines intersect, s plus t equals 10 and 40s plus 100t equals 700. You get this ordered pair right here, which happens to be 5, 5. For this point C, we have the equation s plus t equals 10 and t equals 0. Okay, so here's this line right here. Remember, we got t, it needs to be greater than equals it. Well, that border line is t equals 0. Well, we get an ordered pair for that one of 10, 0. And D, we get the intersection between t equals 0 and s equals 3. We end up with this point D right here, which is 3, 0. Now we find the value of p at each vertex. So we get these ordered pairs, or these intersections. Notice that they didn't take this intersection up here, or this intersection here and here. Notice that these vertexes are in the shaded area, that feasible region, and these become points of interest really to test in our original profit equation. So if we put in the values at these different points, point A is 3 and 5.8, well, you put 3 in for shrubs, right? And you get $10 per shrub, and you put 18 in for the number of trees, in this case 5.8. I'm not sure how you get a 0.8 of a tree, but in reality that's in algebra we end up with that, and then you also have some judgment on whether that makes sense, right? Well, when you put those in, and you get a value of 134.4. In B we have 5, 5. They put those in to this equation, and they get a profit of $140. And in C you get a profit of $100, and D you get a profit of $30. Well, the maximum comes in at this 0.55 right here, and the minimum comes in at point D, which is right here. And those, like we were talking about, now in this case you probably want to know where your maximum is going to be in this feasible region, right? And because those constraints really are real, so we have to consider them, and it creates a model basically with this graph that we can pull out a maximum production or maximum profit possible within those constraints. So that's what they talk about in here. Say, well, we've also shown that profit is at minimum at 30 if we do when 3 shrubs and 0 trees are planted, right? But if we have 5 shrubs and 5 trees, under those constraints, that is the best scenario to get a maximize for that situation with that garden. We can show that we could get a maximum profit of $140. Now this next example is about grading, and this is probably something I should probably make a linear equation about how I grade in this class, right? And we're going to talk about possibilities where you spend your time, though I don't think this is applicable in this case with how I do grading. You think, well, I wouldn't want to spend much time on homework because that's only 10% of your grade, but the process of doing your homework hopefully to 100%, which could take some time sometimes, is going to prepare you for the more heavily graded things, quizzes and tests, right? Well, in this case, Cy here can submit book summaries for 70 points each or research projects for 80 points each. He estimates that each book summary will take 9 hours and each summary project will take 15 hours. Now and at the most he will have 120 hours to spend. Now I wish when I was a college student I was that organized, but this guy is probably going to succeed very well if he can figure out all this stuff, right? Well, he may submit, he's talking about now he said, well, here's what you actually get. If you want to get your points here, you could say, well, you say, well, I could do 100. I could say, well, I'd do 100 research projects, right? And I'd get 8,000 points. Well, it takes time, right? There's some real constraints on things like that. I don't know if he's going to have 1,500 hours to do research projects, right? So he's putting in what he estimated time for each type of thing, and he knows that he's only going to have for this quarter or semester that he's looking at, that he probably has 120 hours he can commit to this history course for this purpose. And also the teacher said, well, I'm not going to spend the rest of my life reading book summaries and research projects because there's some person may just go nuts and enter a bunch. He says the max you can put in is 12 assignments. So how many of each should he complete in order to receive the greatest number of points? Well, there's a lot of information packed in this little paragraph, and we need to familiarize ourselves with this. And they start doing some things that are very important when you're trying to translate from English into algebra, is to find variables. We want to have a variable to represent some important information or some really unknown thing in here. What's he trying to figure out? Well, the number of book summaries he should do. Let's call that B. And R, let's call that the number of research projects. Isn't that the question? How much of each one of these does he need to do to maximize the amount of points he can get? Now Cy is limited the number of hours he can spend, and by a number of summaries and projects he can submit. These two limits are the constraints. They're really inequalities, right? Well, a good way to organize this stuff is to create a table. We have two types of things going on. We got book summaries and we got research projects. Here's what the points you get for each one. Here's how much time it takes for each one. Here is the number that could be completed, right? This is the variables we defined. B represents the number of book summaries actually submitted. R is the number of book summaries or research projects actually submitted. Well, right here we can make an inequality. They tell us that the max, or the sum of these two, the addition of these two, cannot be greater than 12, or has to be less than or equal to 12. Now the total time for each type would be taking the number of completed, well, it takes 9 hours per book summary and 15 hours per research project. Well, these expressions represent the time. If I did 2 book summaries, it would take me 18 hours, 9 times 2. Well, there's a constraint on the time. Is it both of these things right here, the sum of those has to be less than or equal to 120. He says he will only have at most 120 hours to spend on that. Now the points that you get for each one of these things can be put into an expression too. If I wanted to know how many points I get if I put in a number that B represents a number of book summaries, I'd take 70 times the number of book summaries. So if I did 10 book summaries, I'd have 70 times 10 or 700 points created from those 10 book summaries. Well, here is the thing he wants to maximize. He knows how you'll get that. It's going to be 70 points per book summary plus 80 points per research project. This sum right here, which could be very complicated unless you really are really tough to get to this visually and practically translate that into algebra without trying to do some type of method like this table to organize your work. So they take this part right here and says, let's let T represent the total number of points, right? And that wouldn't that be what you get if you added these two things together and you actually did some book summaries and research projects and you want to know how many points he would get? Well, you put the numbers in for those, multiply, and then add together and you get that total. Well, T is your total number of points. Alright, so we have an equation here, right? We have constraints. Now here's these, B needs to be greater than 0. You're not going to have negative book summaries or negative research projects. Unless, if you put in something so bad for a book summary that he actually took a point away, maybe, I guess. But that is not a reality, as you're probably not going to turn in some. So you have positive values for each of this. They could be 0, but they have to be positive. And we graph those. So here's our constraints. Now we're not graphing this. We're graphing the constraints that we talked about in this word problem. And we end up with this feasible region right here. That in this region we're going to have the possibility of a maximum and a minimum. But this feasibility right here, with all those constraints, if I pulled ordered pairs out of here, I could figure out how many points I got, right? Because I'm going to have a number of books, which is my horizontal change, and number of research projects in this case, which is my vertical change. Okay? So we get this constraints. These vertexes here of this quadrilateral four-sided figure is points of interest. So we want to test these actual points in this point equation, right, where we could figure out the total points. So they do some things that we've done before to find coordinates of each vertex in solving a system of two linear equations, right? They want to get actual values, not estimate from that graph. So they put this b plus r and combined with 9b plus 15r equals 120, right? So this is that border to the maximum amount of projects that you can, or book reviews and research projects you can put in, is got to be that 12. Well, the line is represented by this equation, and then here's my amount of time it takes for the books, and here's the time for research projects. Here's the border of that one. It said it had to be less than or equal to 120, but here's the border equal to 20. Well, this line and this line, they both have two equations, so we can say, well, what happens when these two lines intersect? And they pull these two lines again. If we go back and look at this graph, they pull those equations from here, right? So really what they're doing is they're looking at this line right here and this line right here. So in other words, they're looking at point C to find out what the ordered pairs are for this intersection between these two lines. Well, we can do that by what we know about solving linear equations. They use substitution or elimination method, and they take this first equation right here, number 1, they take it times a -9. Why? Because then when I combine these two, it'll get rid of my b, and I end up with an equation with one variable, 6r equals 12, so r is equal to 2. Well, if r is 2, then what's b got to be? I can put it back. I'd definitely use this one, and b has to be 10. So we end up with that ordered pair of 10, 2. 10 represents the horizontal on that graph, right, and vertical. And they do the rest of these, and they get the ordered pairs. So you notice they say the coordinates for C going back to that graph, and so on. Okay, so they do that. Basically, I'm not going to show how they get the actual ordered pairs because we should know how to do that. And then with these ordered pairs, I can go back to the original equation, right, for total points, and that's what they did right here, this table right here. Well, point A vertex is 0, 0. We'd end up with 0 points. If you put in no book reviews and 0 research projects, you're going to get 0 points. Well, B, they take, if I put in 12 book reviews, I'd end up in 0 research projects. It's within the constraints, right? These are on that feasible region. These are the vertexes of the borders of that quadrilateral. You get 840, right? And here on C you get 10 and 2, we end up with 860, and point D, it ends up be 640. This is probably where you want to be if you want to get the most amount of points, is 860. So we know that we can check that the total points is less than or equal to 860 for several other points in that shaded region. This is left to the student. Okay. So in summary, to maximize his points, Cy should submit 10 book summaries and 12 research projects. Now if I did this and I said, well, 860 is not enough points, I don't like that, then I can mess with my constraints, right? I might say, you know, I might have to take 20 hours away from another class and open up that constraint on the amount of time, and that would change some stuff too. So, you know, you hear a lot in algebra, where are we ever going to use this stuff? Well, here's some real world stuff, and I can easily show you without knowledge of how to work with linear systems, how to deal with equations with multiple variables, and all the tools that we've built up to this point. You know, try to explain this to somebody that doesn't know how to graph a line, right? And those kinds of things. So we're building up to the point where we got enough algebra skills to do linear programming, really. And we can bring in and say we can make a better decision about a complex situation by putting this in with constraints. Well, good luck with that. That's the end of the chapter, and we'll do the quizzes and chapter tests soon. Good luck.